Hello students, welcome to section 8-3, quadratic functions in standard form. Today we're going to be taking a look at a continuation of all of our work with quadratics, more specifically how standard form will play into things. How is the standard form of a quadratic function different from the vertex form? Yes, we've already discussed vertex form. Example 1, relate c to the graph of f of x, which is equal to ax squared plus bx plus c. What information does c provide about the graph of f of x, which is equal to, again, ax squared plus bx plus c? So let's start. I'm going to graph several functions of the form f of x, again, equals ax squared plus bx plus c. Look for a connection between the graphs and the value of c for each function. As you can see, our graphs below, as you denote from left to right, the function on the far left has a point of which crosses the y-axis at 0, -3, the second at 0, -1, and the third at 0, 1. So the c value goes from -3 to -1 to 1. Therefore, the functions are all taking shape as follows, noting the very first two terms are identical on every single function, -2x squared plus 4x. However, it's the c value that's different. Okay, when the c value, as you can see, is just simply -3, it's going to cross the y-axis at -3. Similarly, at -1 and at +1, given those two particular c values. C is, of course, what I just said, as you can denote. The value of c corresponds to the y-intercept of the graph of the function, as I already said. I do encourage you to take a look at the triad example below. This is going to be a nice connection to be made later. Always try those if you can on your own. Okay, so let's now take a look at the standard form of a quadratic function. And it's denoted as such. F of x equals ax squared plus bx plus c, where a cannot equal 0. The value c is the y-intercept of the graph. The axis of symmetry of the graph is the line x equals -b over 2a, and the x-coordinate of the vertex is -b over 2a. So we have actually seen this before, and when we've taken a look at this particular equation, again, it was the axis of symmetry we were defining. And notice how both the vertex and the axis of symmetry has the same expression, -b over 2a. And technically this is the x-coordinate of the vertex, if you recall. So example 2. So we're going to graph f of x equals 2x squared plus 4x plus 3. What are the axis of symmetry, vertex, and y-intercept of the function? So as we can see here, step 1 is to find the axis of symmetry, which we'll do using, again, -b over 2a. Turns out b is 4, as you can see, here and here, and then a is 2, here and here. So we go through the process, -4 divided by 2 times 2, which is -1. The x-coordinate of the vertex is also -1. So we didn't just find the axis of symmetry, which again is x equals -1. We also found the x-coordinate of the vertex, -1 comma. We plug it in to find k, if you remember h comma k. We're going to plot the vertex. So let's take a look. What we're going to go ahead and do now is use the x-coordinate of the vertex to find the y-coordinate, using, again, this equation, plugging in -1 as such. Make sure you do plug it in parentheses, as they do here, because otherwise you're not necessarily going to get the correct sign. In particular, right here, squaring a -1 is going to end up being positive, not negative. So be careful with that. In the end, if you do that math correctly, you end up with 1 for the y value, or y-coordinate of the vertex, also known as the k value. So h comma k is -1 comma 1. So the y-coordinate of the vertex, like I said, is 1, so we're going to plot that point, -1, 1. And we're also going to plot the y-intercept and its reflection. So let's start unfolding here and uncovering. The value of c is the y-intercept. Plot 0, 3 and its reflection across the y-axis, or pardon, the axis of symmetry, which is -2, 3. Plot another point and its reflection. We're going to evaluate it. For x equals 1, you'll get 9. And then, as we were going to see here in a moment, and I'm going to uncover more here for you, the reflection 1, 9 across the axis of symmetry is -3, 9. We're going to plot 1, 9 and -3, 9. A lot to talk about, obviously, until we see the graph take shape. Can we truly make that connection clear where we're going to see these reflection points, we call them. And I've even got an XY table that I created for you to take a look at. So if you take a look, it turns out that we have, and I'm going to even uncover even more here. There we go. I got a little Desmos graph I created as well for you. If you take a look at the parabola in fact has a vertex at -1, 1. On my XY table, I have that in the middle of all my points. If you remember in the past, I said 3 points maximum are, or minimum, pardon, 3 points minimum are what you're going to want. Although if you make more than 3, that's fine. I did, though, as far as what the book did as well, I made my points symmetric to one another. In other words, if you pick -1, 1 again as the vertex, which you should, 2 more points to possibly pick are reflection points, so to speak, about this axis of symmetry line. In other words, -2, 3, there it is, and 0, 3. Notice -2 and 0 are going to have the exact same y value. That is called symmetry. Okay. It also just so happens that 0, 3 is the y-intercept. Okay, so you can, of course, observe that from the very beginning, C being the y-intercept, of course. Other points to take a look at, -3, 1, and, or 9, pardon, -3, 9, and 1, 9. These 2 points are also symmetric about that line. One thing to take into account as to maybe why these points were picked and why they serve our purposes well, and that is technically -2 and 0 are the same distance from -1, as are -3 and 1 are the same distance from -1. And you can actually gauge that by virtue of the graph as well. The distance between the axis of symmetry and that point to the left is 1 unit, and the axis of symmetry on the right of that line is this point, which is also 1. So 1 unit left, 1 unit right, and so on and so forth. 2 units left, 2 units right. So you can see that take shape, and of course the parabola nicely takes shape from there. The Desmos graph on the right here, I do encourage you to take a look at. I created that as a kind of corollary to things, just to kind of prove out that you should be able to do this also via Desmos. Please take a look at that. It depicts, of course, all the same nuances that I just did. As you can see, the y-intercept, the symmetric point over here, the vertex, and the axis of symmetry. Let's move on. Example 3. Compare properties of quadratic functions. The trajectory of the water from fountain A is represented by a function in standard form, while the trajectory of the water from fountain B is represented by a table of values. Compare the vertex of each function, which trajectory reaches a greater height in feet. So here's parabola A. You can see that take shape thanks to this equation, -x squared plus 2x plus 8. Over here, I've actually covered up the table, which I'll now uncover for you as follows. The table of values, as always, is a nice way to depict a function, of which you can see at the middle of it all, you have a vertex at -4, 10, which I've denoted as such. I've also denoted, and I had to make a couple corrections here, -5 and -3 are going to both yield 8.75. And then lastly, -6 and -2 are both going to yield +5 as those respective y's. Which tells us, if we take a look actually at this graph more specifically, or equation, pardon, and I guess the graph as well, that you can frame the equation as a vertex form, such that if you plugged in your h value, in this particular case it's a -4, but it's minus a negative if you recall, so it's really +4. You don't know a, but you do know, let's pick -2, 5 for x and y, so we're picking this point. And then we can solve for a, like I said, but one more substitution process, of which we can plug in also 10 for k. If you do the math here, this ends up being 2, of course, so 2 squared, which is 4. I subtracted 10, 5 minus 10 to get negative 5, divide by 4 to get negative 5/4. The equation in vertex form, which you are familiar with, we've done this in the past. Now knowing what our a value is, here's your h, and here's your k. It's actually, if you think, minus a negative 4. Remember that. So negative 4 comma 10 is pulled out of that as your hk, and your a value again as such. Notice both parabolas open down as they should because of the a value being negative here as well as here. Okay, so let's continue. That's a nice kind of precursory step to getting this process started really in full, such that we're going to find the vertex. We already did that, at least for the second graph. The fountain on the left has a vertex of which you can do negative b over 2a. Okay, in doing negative b over 2a, you have negative 2 over 2 times negative 1, which is simply just 1. The vertex on the other function, which I've already denoted up above as negative 410, which of course they do the same here, is, well, the point there in the middle. Notice that the values beyond the middle point are just repeating themselves based upon the symmetry we've discussed. You can also, of course, find the y-coordinate on the first parabola, this a fountain, simply by plugging in 1 for x, and therefore if you do the math you'll get 9. So in just comparing vertices, we can see the difference. Fountain A reaches a height of 9 feet. Fountain B reaches a height of 10 feet. The water from Fountain B, of course, reaches a greater height. Okay, there's nothing really more to do on this problem, even though I did give you guys the equation from Fountain B. If we did need to do more, Fountain B and now Fountain A, we can dig in with a variety of other things. For number 4, example 4, what I'll go ahead and do is get you guys started. It says Mia tosses a ball to her dog. The function f of x, which is this, negative 0.5 times x minus 2 squared plus 8, represents the ball's path. And you can see the picture uncovered. Now, what does the vertex form of the function tell you about the situation? So I would argue, just based upon looking at the vertex form, we already know the vertex. Okay, so the vertex, in other words, this topmost point, should end up being simply 2, 8. That's a very important feature, obviously, to start with. If we take a look, again, we can note, as they do, the red and blue denotations of h and k respectively are again 2 and 8. Since also the a value is negative, it's technically negative 0.5, it's less than 0, we know the parabola opens down. So again, the vertex is at 2, 8, and the parabola opens down. The vertex form tells you that the vertex of the graph is what it is, 2, 8, and the ball reaches a maximum height of 8 feet above the ground, which is 2 feet away from where Mia releases it. Part B, what does the standard form of a function tell you about the situation? So what I'm going to go ahead and do now is I'm going to rewrite. I did some uncovering here already, and I'm going to show some foiling here in a moment. As a matter of fact, why don't I undo that for the moment, just to kind of give you guys some precursory perspective as to why I'm doing that as such. So we're going to go ahead and rewrite this, and I'm not so sure I can do that otherwise, so let's delete that. So anyways, here's my function. Yes, you are going to FOIL to see that you're on track, but if you distribute the negative 0.5 after you FOILed x minus 2 quantity squared, so it is nice to see that unfold as such. So x squared minus 4x plus 4. Then distribute the negative 0.5. Notice the plus 8 is still out on its own. And then you'll combine like terms, and you'll end up with that particular standard form. Why is that important? Here it is again in that particular general format. The y-intercept is 6. The standard form tells you the y-intercept of the graph of the function, which is 0, 6. The ball was 6 feet above the ground when Mia threw it. So if you look back at the picture, this is when she released it at 0, 6, and of course the vertex is there, and you can argue for both equations in different ways being helpful. So that should conclude our lesson today. Please look at the triads as well.